Hi class, this week we are doing a determination of a molar mass of a solute using a freezing point depression. This involves chapter 13, so if you want more information, I suggest you start reading it now so that they may help you understand. I did give a lot of detail in this experiment because we haven't covered this section yet though. So we're working with molality, which is a small m, versus molarity. To make sure you understand, this is not molarity, this is molality. Molarity relies on volume, and volume can change with temperature. So we don't want to do that. We don't want to use molarity while we're actually using involving temperatures, experiments with temperatures. We use molality because moles and mass do not change with temperature. So this is a small m, and what it is moles over solute and over kilogram. Excuse me, let's start again. Moles of solute over kilogram of solvent. So this is not solution. Solutes on top, solvents on the bottom. So there's a big distinction. Make sure you understand. This is not kilograms of solution. This is solvent. So a freezing point depression. Let's look at system A. The particles come together very easily in a pure liquid. If we freeze this, they will come together. There's nothing blocking them. So they will freeze at a certain temperature. Once that temperature hits, these will start forming a solid. System B has particles involved. So what we do is we throw an impurity in it, if you will. It is a non-volatile solute, and this occurs for boiling as well. It will stop or prevent, as long as it can, from the solution forming a solid. So it will force the freezing point to a lower point, which means more energy actually has to leave the system if it's freezing to come together. So think of antifreeze. Antifreeze in your car, it prevents your car from overheating and freezing by increasing the boiling point and decreasing the freezing point. So the freezing point will actually have to be lower than what the actual freezing point temperature is, because it has to overcome these particles that are blocking the way of it becoming a solid. Excuse me. So freezing point depression, use a non-volatile solute, so something that does not evaporate easily. The presence of a solute decreases the temperature at which the solution freezes. The normal freezing point depression can be expressed in the terms. So this is the equation we're going to use. It's delta TF, which is the change in freezing point temperature. KF is a freezing point depression constant. It's specific for each substance. And so there's a constant to it we will have to look up. And then M, small m, this is molality of solute. And this is in your PDF, it's number 2. And number 5, rearranged, if you need to determine the molality, it's moles of solute over kilograms of solvent. Here's an example to help you understand this. So if we look at a solution, and then this is normal without any impurities or anything blocking it. So for water, the normal freezing point is 0, of course we know that, and boiling point is 100. But if we add a non-volatile solvent, particles, to water, we change the dynamic, what's going on with it. So the boiling point will actually increase because the water cannot evaporate at the boiling point that it's used to, because those particles are blocking it from evaporating away. And in freezing, it's standing in the way. So think of people trying to dance, a couple, they can't reach each other because of the fact that there's too many people in the way. They have to work harder to come together. So you can see that it lowers the freezing point from the normal, and it increases the boiling point. So it has to actually hit a higher temperature for water to boil, because it has to overcome those impurities in it. So freezing point, solvent molecules prevent the solute molecules from forming. Has to reach a lower temperature. The solute will not enter the solid structure. It's usually energetically unfavorable because it has to work harder to do that. And remember, as a freezing, it has to remove energy in order to come together. But in this case, it has to work harder with more energy to come together. The freezing point lowers to compensate for the solute molecules preventing the solid forming. This is called the freezing point depression. And the change in freezing point is proportional to the amount of solute, which makes sense, because if you add a small amount, then the change in freezing point will be very small. If you add more, the change is going to be a greater change in that freezing point. This is why salt is added to water in cold areas that, Chicago and so forth, I guess. I don't know. I've always lived in LA all my life. I don't deal with any of that stuff. But here, this is a good example. At another college, we do this lab, not this exact lab. We do a lab similar to this, and they have to graph as well. And this is what they have to graph is you have a pure solvent and the freezing point. Then they add an addition of a certain amount of a non-volatile, solution with particles, particles in it. Sorry, I'm kind of stuttering here. And you can see the freezing point is changed. It's lower. And then they add more, and it's even lower than what the original freezing point is. So it's blocking that from coming together. Freezing point depression is an example of a colligative property. That means, and this is hard for students to understand, is that it's affected by the amount and not the identity of the solute. You do not know what the solute is. You will not know what the solute is. Yet we will know the moles, the molar mass. We will get everything from this and never know what the solute is. Colligative properties depend only on the number of solute particles present and not the identity. There's no interaction between these, the solute particles and the solvent. They simply are colliding. They're blocking. They're not. There's no strong interaction between them at all. Freezing point is very useful for things discovering the molar mass of compounds, antifreeze, melting snow, so forth, making homemade ice cream I've never done, and so forth. So colligative properties do not need to know the identity of the solute. What they involve is, colligative properties include freezing point, boiling point, vapor pressure, and osmotic pressure. Okay, so colligative properties include freezing point, boiling point, vapor pressure, and osmotic pressure. Anything else for this lab, we don't count. This is the 4 that we are involving with colligative properties. Equilibrium. So when a freezing point of a liquid and the melting point of a solid occur, they occur at the same temperature, and the temperature is defined at the point which a solid and liquid phases coexist in equilibrium. And equilibrium means that the number of molecules leaving and entering the solid phase per unit are equal. So you see some are going into this phase and some are going, and they're going at the same rate. So this is what we call equilibrium. I'm going to discuss this further. This is just an introduction to it so you understand somewhat of what's happening here. We'll come back to that. Freezing point depression constant on the solvent. Now the wording here is very important because you can make some mistakes because you didn't dissect the wording correctly. And with chemistry, that's very easy to happen. So I want to give some examples of this. The change in freezing point is proportional to the molality. That's because of the particles. Kf is the molal freezing point depression constant of the pure solvent used in the experiment. Solvent, not solution. The molal freezing point depression constant is unique for each solvent. So water, we have it here. It's 1.86 C over M. That's the units of C over M. This is the equation we want, and I've already broken these down. So this is for water, and most of these examples I'm going to show you are for water. So if we look here, this is a chart I found. I blocked out the boiling point ones because we don't need these. We're looking at Kf, and you can see water, benzene, and a couple others here, and you can see the Kf that goes with it, and these are the units that go with it. For this lab, the freezing point, we're going to use stearic acid, and stearic acid is the solvent. We do not know what the solute is on this, and we will not know. The Kf is 4.7 Celsius over molality. Okay, so I suggest that you write down the Kf for stearic acid because for some reason it's not shown anywhere in lab flow, at least not that I can find. And you're definitely going to need this for the lab. We don't care about the freezing point, honestly, but you definitely need the Kf for the our calculations. Van 't Hoff factor. So I have shown you prior to this, I showed you guys this equation, and this is correct. However, it's not completely correct. I omitted an I. And most of the time when you see this, you will not see the I. The I is the Van 't Hoff factor, and this only involves electrolytes. And I have in parentheses where they are, but you may be given problems that involve electrolytes, and it's not stated that they're electrolytes. You just have to know that. And when you're dealing with electrolytes, because the electrolytes disassociate, that means that you're going to have to add an I here, because this I will definitely affect your numbers, and they will be wrong if you forget it. So let me explain here. The I is the factor, this factor equals the number of ions produced from each molecule of a compound upon dissolving. So it has to dissolve, it has to dissociate, and as we've already discovered, not all compounds dissociate. So here's a thing. Look at what you're being asked. Is it an electrolyte? Does it dissociate? You need to add the I. If not, the I is usually left off because we don't deal with not all compounds that we're dealing with dissociate. So a 1 is for methanol because methanol does not dissociate. So that's why it's usually left off, because this number is usually a 1 on here. But if you have calcium chloride, this would be 3. It would be 3 because calcium is 1 ion as it dissociates and chloride is 2. So that's a total of 3 ions, and this I number would be 3. Sodium chloride is 1 and 1, so this I number would be 2. And calcium phosphate would be 5, because if you count this all up, these are going to be 5 ions. So if we look at this, what does this do to the freezing point of a solution at calcium bromide versus glucose? Freezing point will be lower for calcium bromide because it has more particles. The more particles will stop that solution from becoming a solid. So there's more particles to block it. Where glucose is a molecule, it does not dissociate, so it doesn't have more ions to stop. So the freezing point will not be as large. The freezing point will be lower for calcium bromide, or think of larger. There would be a larger difference between what the original freezing point was to what the freezing point is now. A larger Van Hoff for calcium bromide is I equals 3 compared to glucose, which is I equals 1. Calcium bromide has more ions, which I already stated, more ions blocking the particles from coming together. Here's just another example of it. So 1 mole of sugar, 2 moles of dissolved particles, and 3 moles of dissolved particles. So this potassium sulfide has the most particles, so that will have a lower freezing point than the other two because it has more particles to block the solution from coming together. Now let's get to some problems. I have in parentheses that this is an electrolyte, but you will not be. If you're given problems similar to this, you're going to have to make sure you figure that out or you're going to get the wrong answer. So before you do anything, look at what is being asked, look at what the compound is, and does it dissociate? Is it an electrolyte or is it not? If it's not, you're fine. But if it is, you need to have the Van Hoff factor in with the I. What mass in grams of sodium chloride needs to be added to 1.7 kilograms of water to create a solution with a freezing point of negative 6.4 degrees Celsius? The freezing point depression constant is given. Okay, so let's break down everything for this problem. We have the problem here. It's electrolytes. We need the I. The difference, the difference in the freezing point is negative 6.4. We have an I equals 2 because this associates into 2 ions. And we have the KF factor. Now in your PDF, you are given, for equation 1, how to get rid of negative numbers. So if you see a negative number, we don't use negative numbers here. So if you're given a negative, you need to get rid of it. And the first thing you need to do is understand this is a solution. So, because why? What mass in grams? So this is the solute and this in the water. So this is a solution. So this is going to be added to, this is a, this one should be up here, it moved. This is equation in your PDF. You would put that negative number here for solution. 0 is the solvent. Why would it be 0? Because we're dealing with water, which has a freezing point of 0. And then you can take care of this, and now you have a positive number. So when you read this, are you dealing with a solution or are you dealing with a solvent? That is one of the small discrepancies that can mess you up with negative numbers, trying to figure out how to get rid of this. Look at your PDF, look at my example, and then figure out if it's a solution or a solvent, and you can usually just get rid of it by doing a simple plugging it into a formula. Okay, so the moles is here. I'm going to put an X for the moles because we don't know what the moles are. We don't know how many moles. We are only given a value of the solvent. So I'm going to X is our moles. So I'm going to plug it into this equation here. So we have 64 now equals 2, which is the I. This is the KF factor, and then we have our, what we want is our molality here. And then we just solve for X. So you start moving everything around. So right here was our actual number. I did it in bold, but I took it past one more step so we can get to the mass that we needed for this. Excuse me. And I accidentally did not cancel this moles out right here, but because this is moles and this is moles. So this should only just be grams, but I made it into a molar mass, and that's a mistake. So we would have solved for moles, which is in black, and then we would have used the molar mass of salt, and that would have given us 171 grams. And forget this last portion here that I accidentally didn't remove. But the mass is not, I mean, the calculations are easy. The hardest part is plugging in where you need to plug things in and deciphering what's being asked. But really, once you start doing these or looking at them more and more, they're not that difficult. Okay, so what is the molar mass of an unknown compound? So 25.3 grams of an unknown compound is added to 0.200 kilograms of benzene. With the added solute, the freezing point depression is 3.12 compared to pure benzene. What is the molar mass of the unknown compound? This sounds very, very confusing. It's not. We're using the same equation. We just have to pull everything out. So in this case, I'm going to put the grams over, which so we have grams over mole because the moles are what we don't know. So this would be like a molar mass, and then the solvent. And we're just going to solve for X. So here's the freezing point depression. Here's the Kf factor. We're not told what it is, so we don't have to worry about the Van't Hoff factor, because if it's a Van't Hoff, you're always going to be told that it's, calcium bromide, sodium chloride. You're going to be given something to let you know that, not an unknown. And so we just solve for X. So you start moving things around. Now the key thing here is I want to point out that, let's get to this. We divide this, we bring this over, right? And we leave the kilograms on the bottom. Now when you get to this point, you cancel these C's out, and it's going to give you one value. Once it does, take this mole and break it out into moles per kilogram, and that will allow you to bring the kilograms over and cancel out the kilograms, leaving you a mole. And then you can solve for X, and it'll set it up where you'll have X on one side, and you can bring the moles underneath the grams, and it'll give you the molar mass. So just take your time understanding how I did this, but definitely once you get this isolated to an M by itself, break it out into the actual formula, so then you can see why you're canceling out kilograms and so forth. Okay, what is the freezing point of 3.51 kilograms of water if it contains 165 grams of calcium bromide? I put in parentheses as an electrolyte. You will not always be given that hint, but here's the thing. When you're dealing with electrolytes, they tell you what the solute is. They don't leave it unknown like in the previous problem. So this one tells you have to use I. You should instantly know, I have to put the I there. So the freezing point depression for water is 1.86. That's the solvent. So in this case, all right, so let's take a look at what we have here. We don't know what the delta T is. We have I equals 3 because this disassociates into 3. And we're given 165 grams, and I just jumped a step by using the molar mass, and so this ends up being 0.8254 moles. I really didn't worry about sig figs here. And I plugged that in, okay? So what did I do here? Oh, I'm sorry, this thing moved. This kilogram should be here, and this should be up here. I checked this again, and it still moves. Sometimes I don't catch everything. The molality of this is 0.8254 moles, and we're given the solvent. So this actually goes here. This is our answer in bold. So the molality for the solution is 0.2351 molality. Okay. So now let's plug it into the problem. So the delta T we don't know. We have a 3 for the I. We have the Kf, which is 1.86. And then we have the molality of this. So we're going to work this out. And when we work this out, it gives us a delta T of 1.31 is the difference in temperature for the solution. Now, we don't want the solution because this is asking for what is the freezing point of water if it contains, so I'm jumping ahead here. So here's the solution. But the delta T is not with the solution. We have to actually work with the solvent and the solution. So you take the water, which is here, minus the delta TF for the solution, and then we plug that in, and it should be negative 1.31. The value they gave us was a positive number, which we can't have since water freezes at 0. So if this seems confusing to you, let me take a step back. Water freezes at 0. So if we were looking for a delta T, the delta TF is the temperature freezing point difference. But this should have to be a negative number. Why would it have to be negative? Because the negative, it has to be below 0. And this wasn't. It's telling us the freezing point depression is a positive 1.31. But if water freezes at 0, it can't freeze at 1 degree. It has to be below that. So that's why we plug it into the equation. And now it gives us a negative 1.31, and that is a freezing point depression. It went down below 0, and it gave us a negative value number, which is what we needed on this one. So if this is confusing, please take a look at this one and look at the difference of where I plugged it in with this one. We need a lower number for water that's below 0. We can't have something above it because that's still liquid. This is a lab that I do at another school. This is not the same here, but you kind of get this is how we set it up. Is we have a bunch of ice, and then we get the freezing point temperature of the pure solvent, and then we add an unknown solute to it, and we keep track of the time, and we determine the freezing point again. So in your data point, in your PDF, this is an example of what you're going to be given. You're going to be given a whole bunch of data points with time and temperature. You're going to have to graph these. This is why I was looking for somebody who understands Excel, because if you don't, you're going to need to learn Excel. And I strongly recommend, if you do not know Excel, you should, because chemistry loves Excel, and the more classes you have to take in chemistry, you will use Excel all the time. So it's something that you're expected to know, and I strongly recommend that you do. This would be a good point if you're not understanding it. The internet's full of videos. I have posted a couple videos to help you, but you definitely should know how to be comfortable with Excel. All right, so cooling versus freezing areas of a graph. This is a key point in your graph that's going to happen. We're going to have a curve, and then it's going to flatten out. And that is the freezing point of the liquid and the melting point. So this is the equilibrium. And you're going to have this point in your graphs, and I'm going to show you what this is. So you're going to take, this is from your PDF as well, you're going to take all these data point numbers that you're given, and you're going to graph them in Excel. You're going to pay attention to the instructions it's giving you, because this here is going to give you this. That's why there's 3 columns. The first column is the temperature. The second column is temp readings, which difference in successive readings. This is time. This is second column here. Which are greater than 0.5 degrees Celsius. So if you add these up, they're all a difference of 0.5 degrees Celsius. Third column, this should say third column. This was a mistake. Temp readings, which are difference between successive readings, are less than 0.5. So here's an example. These two, 59 and 58, there's a difference of 1 here. But if I take 58 and 57.8, there's a difference of 0.2. So we leave this one because these two numbers are still large. But the minute I get one that's not less than 0.5, that bottom number comes here, and I create a second graph. What this means is that the cooling temps end at 570, and then the freezing points start at that point. And that gives you this quick line in the graph. And you can graph the whole thing at once. So when you write these down and then you take the whole thing, you include the whole thing, you highlight the whole thing and then hit scatter plot, it'll graph it without you. It'll look, this is my graph right here. So this blue is these parts. These are not my data points, but this blue is these points here, and the orange are these points here. Still one graph and still one experiment. This is what's given to you in the PDF. Why are you doing this? The whole thing is we need these equations. We need these equations in order to solve for information that we're going to have to enter into our data. So when you graph this, it should have a title, it should have temperature, it should have, this one is missing Celsius, so this is definitely should show what units. Time is seconds. It should have it should have trend lines. This trend line goes for this one here. This trend line goes for this one here. And since even though these are in one experiment, you will be given an equation for the freezing portion and the cooling portion. And these instructions are all here in your PDF. Okay, so I'm going to show you why you need this. So once you graph it, you're going to have two equations. this equation here and this equation here. So in your reading, it shows you why. You're going to solve for x. So you're going to take these two equations and equal them to each other. So your this negative 0.0496x, and then you're going to have this one, remove these y's, and then equal it to each other. So that's what you're seeing here. And then you just solve for x. And this tells you that the time is 532 seconds. You're now going to take this value here and plug it into either of these equations that you have. And that's going to give you the temperature, because you're going to solve for y. So the freezing point of the solvent is determined to be 57.7 degrees Celsius at 532 seconds. These two calculated numbers you're going to need. So this is mine. I'll give you an idea of what it looks like. This is my second table. So this is with my unknown. So I have a freezing point, my orange here. This is a trend line. This is the trend line here. So it just keeps going where it's at. And this is my equation for my cooling. My orange is my freezing. Now, you're going to have two graphs, because you're going to have one with the pure stearic acid, pure. You want to get the freezing point of just the pure stearic acid. And my second one, which is shown here, is with the unknown particles in it. And I should have a difference of freezing point temperature in these. Sorry if I seem out of breath. I've been doing videos all day long. I'm tired. Okay, so what I did here is I broke out everything that you're going to be asked in the second part, so you don't have to figure out what they mean. So I'm giving you a copy of mine so you guys can see mine, and everything that's being asked here minus the calculated. So the calculated is actually the calculated, and this is solving for x and y. So these are what x and y are for both of them. So this is the first curve, which is just the stearic acid alone. This is my stearic acid with the unknown. And you can see what these mean. Final time in cooling, so this is where the graph ends. And then you have your slope of cooling portion. So this is my slope of cooling portion. You can see it's negative 0.289, negative 0.289. And then my y-intercept is right here. You can see that there. My slope of freezing portion, so same graph, but now I'm taking my freezing portion, and then here is my y-intercept for my freezing portion. And then the last two are my calculated answers that I would have gotten from doing this here. So that's what these are. So you can answer all these. Now you're going to need these calculations at the bottom. This isn't done. You need to take these and you're going to use them. Then the second graph, you're going to do the same exact thing for that second graph. So you're going to have the same data for two. So here is my information of breaking down for each graph. So you can check here. I gave you both graphs so you can see the values and my equations and how I plugged them in. So you can see that information. Now, second part of it, you're going to be given some information, and I labeled these so you can see all of how to answer these. So you're given some information right off. You know, you subtract these to get the mass of stearic acid. My unknown number I covered. Massive unknown, so you're given this, and now you have to enter everything else. 6 and 7 are your calculations, what you calculated for x and y. 8 is the difference between these two numbers. Okay, so that's what I gave you here. That's I broke it down on another page. And then the last three, if you can see here, are molality, moles, and molar mass. Now, with these, I broke it down to show you how I solve for this. I don't know why they put it in these weird orders, but I would do 10 first. Why would I do 10 first? Because it gives you the moles. And once you get the moles, you can finish 9 and 11. You can't do 9 because you don't know the moles, so you have to get it from here. So you can see how I broke it up doing this. So I have my KF. This is why you need the KF. My kilograms of solvent are my stearic acid here, changed to kilograms. And then my temperature difference is the difference of my calculated x and y from two graphs. Sorry, this is y's. My two graphs, you can get the temperature difference, and that is why you need it. So, and it's all explained here if none of this makes sense. And then you can see I solve for x. And then once I get my moles, I plug them in so I can get my molality. And then once I get my moles, I can plug it in because I'm given my mass of unknown, and I can get my molar mass of the unknown of my unknown compound. So that's how you enter all of these. It's the same equation, it's the same steps, they don't really change, but deciphering with the negative kind of messes people up. So take your time in understanding that portion. But really, this is not an overcomplicated lab. The hardest part for some of you is graphing. And the graphing you honestly, absolutely should know. Do not pass this up, because if you continue on with chemistry, you will have to graph, and you will be expected to graph. And there are no classes for Excel in chemistry. Something you're going to have to take responsibility to learn. I did post some videos to help you understand to graph. Okay? And let's see, data report submission. You need 2 graphs. You absolutely need 2 graphs. You will upload them. You have 2 attempts for this lab. Can be a really confusing lab, but honestly, in my opinion, it's not as hard as other labs you've done. It really isn't. And I specifically have tried to break down things as much as I could to even help more. Everybody's solvent will be stearic acid. You're not going to know what the moles are of your unknown. Again, I posted 2 videos. If you don't like those videos, enter scatter plot graphs and look and see. I'm sure some of you guys can find better videos than the ones that I had. I tried to find some that went straight to the point without all these long details in the beginning. And just remember, chemistry loves Excel. So you need to make sure you are very comfortable using Excel or Google or something that, I forgot what it's called on Google Sheets. Something that you should know how to do this. This is one of these expected things without them telling you that you should know how to do this. Okay?